Well, thank you very much. Thank you to the organizers for giving me a chance to talk about my work. So our contribution is on the log-determinant divergences, kind of a generalization of the log-determinant divergences from the setting of SPD matrices to the infinite dimensional setting, namely the positive inverse Schmidt operators. So the generalization, this is what I just said. So the motivation for this contribution is actually it comes from applications in machine learning and pattern recognition, computer vision. So I'm not going to talk about the applications here, but I'm just talking about like, the mathematical formulation. So so this is the outline of the talk. First, I'm going to give a very brief summary of the alpha beta log determinant divergences, which is a very general family of divergences between SPD matrices, and then I will talk about kind of the infinite dimensional generalization of these divergences. So I will talk about the positive definite inverse Schmidt operators and the kind of the affine variant Riemannian metric on this set of positive definite operators, and then the kind of the alpha beta log determinant divergences, first in the trace class setting and then in the inverse Schmidt operator setting. So the alpha beta log determinant divergences on the set of n by n SPD matrices is a very general family of divergences, and it's given by the formula above, where alpha and beta, I'm just using alpha and beta greater than 0 here, and they have the limiting cases when alpha go to 0, beta go to 0, and when alpha and beta both goes to 0. This is also valid for alpha and less than 0 and beta less than 0, but for the case when alpha and beta have opposite signs, the formula is not it's not valid for it's not like a divergence for the whole set of SPD matrices. So I would like to generalize this, and it's a very general family of divergences because actually it covers a lot of distances and divergences between SPD matrices. So the first one is when the case of both alpha and beta go to 0, it's corresponding to the square, or half the square of the affine invariant Riemannian distance, which is like the geodesic distance induced by the affine invariant metric, Riemannian metric on SPD matrices, which is a very like kind of classical metric on SPD matrices. And one other case is the so-called the alpha log determinant divergences. So it's given by the second formula, and it also has a limit when alpha 1, 0, and 0, 1. With this, like this formula here, for example, is the Berg divergence. So it covers, and in the case when alpha equal to it's actually alpha equal to 0. I'm sorry, not alpha equal to a half. Alpha equal to 0, we have something called the symmetric Stein divergence. It's actually very popular, used in many applications in machine learning, computer vision, and in statistics. And so it has like a pretty nice formula over there, like log beta A plus b over 2 minus half log beta AB. So the square root of this has been shown to be a matrix. So it was shown in 2012 by Sra. So it's actually a pretty hard thing to show that it's actually it satisfies the triangle inequality. So this has been generalized to the case for alpha, for any alpha, in the case by Joki and Kruchis and Amari recently. So the square root of d alpha b is also like a metric. So it's a very general family of divergences, and we would like to be able to generalize it to the infinite dimensional setting. As I said, like my motivation is actually in the case of covariance operators. So they are all affine invariant, and actually they induce like the Riemannian metric, the affine invariant Riemannian metric. So if we take the Taylor expansion of the divergence, and the second term in the expansion actually corresponds, like the coefficient actually corresponds to the inner product on where A and B here are actually as AB. So P here is an SPD matrix, and A and B are on the tangent space of the tangent space at B. So it corresponds to like the Riemannian metric on the tangent product on the tangent space at B. So they all induce the affine invariant Riemannian metric. So now let's talk about the infinite dimensional case where we have I'm talking just about the real case here, where H is an infinite dimensional separable number space, and A is about a linear operator. So a positive definite operator has a stronger definition than in the finite dimensional case as given by the quadratic form of X. ax is actually greater than or equal to max squared for norm x squared or for ma is greater than 0. So if a has an eigenvalue, for example, the eigenvalue actually has to be bounded below by ma. So it's a stronger condition than in the finite dimensional setting. And in particular, if a is compact, because trace class or Hilbert-Schmidt operators, and because the eigenvalues are going to 0, so they are actually not positive. They can be strictly positive, but they are actually not positive definite. So Laroton has done the work on defining the affine invariant Riemannian metric on for positive definite Hilbert-Schmidt operator. So what he did was actually introducing something he called the extended unitized Hilbert-Schmidt operator. So he considered the set of extended Hilbert-Schmidt operators of the form A plus gamma I, where A is Hilbert-Schmidt, and we add like the basically a regularization term gamma I, and so this one can be given like an inner product. It's going to be extended Hilbert-Schmidt inner product. So basically, it's given by the inner product of A plus gamma I and B plus mu I, which is given by the Hilbert-Schmidt inner product of A, B plus gamma mu. So basically, by this definition, actually kind of in this definition, the identity operator is actually orthogonal to the Hilbert-Schmidt operators. So along with this inner product, we have the extended Hilbert-Schmidt norm. So it's given by the square norm of A and then plus gamma square. So in this definition, if A is equal to 0, then we have to take the square norm of gamma is equal to gamma square, or basically the inner product, the norm of the identity operator is equal to 1. So it's a form of compactification, because if we take the inner product, because the Hilbert-Schmidt norm of the identity is actually equal to infinity. So we're kind of we're compactifying it. So then with this with the set of extended Hilbert-Schmidt operators, we have a set of positive definite operators, which are like the positive definite operators of the form A plus gamma I, where A is just a salvage operator Hilbert-Schmidt. And this is the infinite dimensional Hilbert manifold. So it's a subset of this set of extended Hilbert-Schmidt operators in the tangent space. Basically, is given by this expression here, just A plus gamma I, where A is the Hilbert-Schmidt operator, which is a self-adjoint. So basically, we just have like, the term. The most important thing is that we have the kind of the term A plus gamma I, and then we have the extended Hilbert-Schmidt norm. So the affine invariant Riemannian metric has basically the same form as in the finite dimensional setting, except that we have the extended Hilbert-Schmidt inner product and the kind of extended Hilbert-Schmidt operators. So it can be shown to be Katanan-Hadamard manifold. It has for non-positive curvature, and it has between any two points. There's a unique geodesic, and the Riemannian distance also has the same form as in the finite dimensional setting. Except we have it has this form here, as we use the extended Hilbert-Schmidt norm. So what we would like to do is actually we would like to have we have like a family of divergences that basically in the same way as in the finite dimensional setting, that kind of in the limit which it will go to this formula when the parameters go to 0. That's what we would like to do. So I'm going to do it first for the trace class setting. So if we have so this is very simple for you. So log n of A just will do the trade of log A. So if we want when A is infinite, we have when A is a compact operator between two an infinite dimensional Hilbert space, and then lambda k the eigenvalues lambda k go to 0. So we have the trace of log A is actually equal to negative infinity, which is another good thing. So we would like to be able to extend in the same way as in with the extended Hilbert-Schmidt operators. We're going to do the same thing for the trace class operator. So we introduced something we call the extended trace class operator. It's actually a pretty simple concept. Basically, we have the set of extended trace class operator just A plus gamma I, where now instead of Hilbert-Schmidt, A is in trace, A is a trace class operator, and then it's become a function out of the extended trace class norm, just given by the trace of A, and then plus gamma I. So we have the extended trace. The same, like pretty similar to the case of the extended Hilbert-Schmidt operator. So now here we define the extended trace of the identity operator to be 1 instead of the usual trace, which is infinity. So given this, we can also define like the set of positive definite extended trace class operator to be just like the A plus gamma I gamma A is a joint trace class operator. And so this one is actually a strict subset of all the positive definite inverse operators, so it doesn't cover the whole manifold. And now, given with this definition, the log of A plus gamma I is well defined, it's bounded, and the extended trace is finite. So with this, we can actually define the determinant. We can define some form of determinant. Now, we have the classical Fredholm determinant, which is given if we have a it's well defined for operators of the form A plus gamma I, where A is the trace class operator. Now, it's not defined for operators of the form A plus gamma I. So what we would like to do is actually we would like to be able to define for A plus gamma I. So we introduce this concept of the extended Fredholm determinant. So it has the forms given by it's a generalization of the finite dimension setting. So it's kind of the exponential of the extended trace of A plus gamma I. So it's well defined when finite dimension setting, which is said to be the regular determinant. In terms of the Fredholm determinant, it's given by, so the data x of A plus gamma is gamma times A over gamma plus I, and it reduces to the Fredholm determinant in the case when gamma is equal to 1. And then we can actually, so this is the definition for all the positive definite trace class operator, but it can be extended for all kind of extended trace class operators where when gamma is not equal to 0 using this factorization property. So, to define the determinant, we actually want to be able to define the, we have to generalize something because the Kifan's inequality for the determinant. So it's given by the formula over there, and in the infinite dimensional setting is actually a little more complicated, so it's given by the red form there. It reduces to a form similar to the finite dimensional setting when gamma and mu are the same, which is the last line here. So we have the same form as the classical Kifan's inequality. So by this, using this property, we can define the alpha log determinant divergences, the alpha log determinant divergences for between two positive definite trace class operator. So it's given by this form. This form is greater than or equal to 0 and equal to 0 if and only if A plus gamma I, A is equal to B and gamma I is equal to B. So it comes from this inequality here. Okay, now because I think I don't have much time, so I probably will skip the next few slides. When gamma is to mu, I will not skip this slides. When gamma is equal to mu, basically it reduces the form to a very similar form to the finite dimensional setting. And in the case when AB is SPD matrix, we say gamma to be equal to 0, and then we obtain the finite dimensional formula. And we can take the limit as well when alpha go to -1, and we take the limit when alpha go to +1, and we have basically, we can recover the finite dimensional formulas using this formulation. Now, okay, I will actually skip the next few slides because I don't have much time. But anyway, I just want to tell you that in the case of RKHS covariance operators, they actually have a closed form formula. Can be computed using the Gram matrices, just to show you that actually they can be computed and they can be applied in practice. So for the alpha and beta divergences, we have a new coefficient beta here, and I have something this factor, this quantity r here, which is not equal to 0. It can be a function of alpha and beta. So this formula is a little bit more complicated, but it's like basically it follows the same line of reasoning as before for the alpha divergences. And it can be shown to be greater than or equal to 0 and equal to 0, but equal to b and alpha, and gamma is equal to mu. So it covers the alpha log determinant divergence when beta is equal to 1 minus alpha and r is equal to 1. And when gamma is equal to mu, and r is equal to alpha plus beta, then it has basically a very similar form to the finite dimensional formula. And if we have AB belong to SPD matrix and gamma equal to 0, then we recover the finite dimensional case. So, okay. And basically, it also induces like the affine invariant Riemannian metric, where AB here just class a symmetric operator. Okay, so now these are only for trace class, like for positive definite trace class operators. If you want to do it for positive definite Hilbert-Schmidt operators, we need a more general concept of the Hilbert-Kalman determinant. So if A is Hilbert-Schmidt, then A plus I exponential the negative A is the term has a form like I plus D would be stress class operator. So we can define the Fredholm determinant with this operator. So we can define the Hilbert-Kalman determinant is given by this formula over there, 2 over there, and then we can define it. So it's not defined for operators with the form A plus gamma I. So what we do is actually we define the extended Hilbert-Kalman determinant the same, basically along the same line of reasoning, except that we define it in terms of the extended Fredholm determinant of A plus gamma I exponential negative I over gamma. And then if gamma is equal to 1, then we recover the Hilbert-Kalman determinant. So in the so this is the formula. It has in the case where alpha and beta are both greater than 0, but it actually has the same form as in the case of the positive definite trace class operator. But in the limiting case, in the two limiting cases when alpha go to 0, beta go to 0, and alpha go to 0, we actually need the Hilbert-Kalman determinant, which is the extended Hilbert-Kalman determinant. Is like the second term over here. Okay, limiting cases. Okay, this is the most important limiting case that I care about. Is actually where alpha and beta both go to 0. So the limiting case is given by the second term here, where this is actually the affine invariant Riemannian distance between A plus gamma I and B plus mu I, where we have like the factor of r prime 0 squared over 8 here, and then we have 1 I equal to 2 alpha, which is going to be sized with the same form as in the finite dimensional setting. Okay, so it has examples. Positivity, dual symmetry, dual inverse, and affine invariance. So I have told you, sorry for the very fast talk. I have told you like about the kind of our attempt to generalize the alpha-beta logarithm and divergences to the infinite dimensional thing of positive definite Hilbert-Schmidt operator. So we talk about the extended trace class operator, extended determinants, and then so it's actually it's a general family of divergences. It encompasses like many divergences and distances. And so, okay, so there are many things that actually are kind of like ongoing work. So the first one I think, which is actually for me so the most interesting, is actually kind of from a theoretical viewpoint, is the connection with divergences between Gaussian measures on Hilbert spaces. So actually I have results for the case where a positive definite trace class operators. So they should be coming up pretty soon, and then because actually in the formulation I was kind of talking about this quantity R here. It just somehow came up in the mathematical calculation actually, but I don't have any interpretation for it, not yet. And so as I said, actually the motivation is actually for this formulations actually come from applications in machine learning, computer vision, and image processing. So some applications actually have been carried out because we have a kind of closed form formula. So many things actually can be computed in closed forms. And of course, like there's also like the very important question of choosing which divergence is the most appropriate, because you have so many divergences. So thank you for your attention. Any questions?
Remarks? Questions? Can you have some reference maybe or examples in machine learning theory for this choice of divergence of this something?
So people are trying to learn the divergence actually in the dimensional setting. But somehow like at the moment they are not satisfactory yet. But they are trying to learn which divergence is.
And you said you had some closed expression for LKHS covariance of radicals and the divergence between them.
Right. So this is the expression. Right.
Action. Right. Okay. Thank you very much. So